Hi guys, Mr. Ramsey here, and this is the background to the chromatography lab that we're getting ready to do. So let's take a look at it together here. First of all, let's talk about just a definition for the word chromatography. Literally, it means, from the Greek language it comes from, to write with color. But for our definition purposes, chromatography is a set of lab techniques that allows the separation and identification of chemical compounds. So you'll need to write down that definition and have it in your notes. We're going to use some different types of chromatography, and the first type we're going to use is paper chromatography. The chromatography, the key chemical process is separation, and so in your notes you'll want to underline that term or that word separation, because that's what chromatography allows us to do. It takes a chemical compound and it separates it into its parts so we can identify that compound. How is white light, for example, separated into the colors that make it up? What is the device that allows us to do that? Light shines through it, it breaks it down into the rainbow of colors. Do you know what that is? Yes, it's the prism. You're awesome. Chromatography was first developed by a Russian botanist whose last name I don't know how to pronounce. But in 1903, what he did, he was actually a botanist as a plant scientist. He actually took a group of plant pigments and in a column of calcium carbonate made an attempt to just separate them out, and sure enough they came separated out into a column of different colors, and he realized that those colors represented different chemicals within the plant compound, and that's where the technique was born. You're going to be creating a set of chromatography standards in this lab. Standards are actual separated compounds that then can be kept as references for identifying unknown compounds in the future. So the little strips of chromatography paper that you're going to use, you're going to separate out the compounds within an ink sample on each of those. You're going to tape those onto your lab, but then later on, once you receive it back, you're going to store that in your notebook, keep it as a standard, so when you receive an unknown ink sample, you'll be able to compare it to the standards that you've created that you have in your notebook, and hopefully then be able to identify the unknown ink sample. One of the things you have to know how to do in chromatography is calculate RF values, because samples look a little different, but their RF values will be in the same range. RF value is just the chemical distance, in other words, the distance the chemical travels up the paper over the solvent distance, which is just the distance that the solvent, and in our case it's going to be alcohol, just simple alcohol. You're going to measure the distance the solvent travels. So therefore the chemical will never travel farther than its solvent, so RF value will always be less than 1. Let's look at this example. If we look at the chemical that's yellow in this example, which is right here, see the yellow thing, it's traveled about 14 centimeters. The distance the solvent traveled is about 18 centimeters, or millimeters, I'm sorry. So in this sample calculation, let's look at it this way. If a spot moves at up 3.05 centimeters and the solvent front travels 5.33 centimeters, the RF value would be the 3.05 that the spot or the sample traveled. Okay, the chemical distance is 3.05. The solvent distance is 5.33. Therefore, the RF value, if I get my calculator out and divide 3.05 by 5.33, is 0.572. Okay, the units of centimeters cancel out, so there are no units for RF value. It's just a reference value, so it has no units to it. See if you can calculate the RF value for the green chemical, okay, and then the red chemical. The solvent distance in this example is 10 centimeters. For chemical green, the chemical distance is 2 centimeters, so divide 2 by 10, and that will give you an RF value of 0.2. For this chemical, the red one, you may have to measure it. If we were doing the orange one, it would be 4 divided by 10, and I hope you see what we're trying to do, how to create RF values. Here's an example of what you're going to be doing today or in the lab tomorrow. You're going to take an ink sample that looks like the sample here on the left, place it in the solvent, which is alcohol, And then over time, you can see there's the solvent front, and the chemicals are starting to separate and travel. Once your solvent reaches almost the top, within about a centimeter of the top of the paper, then it is finished, and you're going to pull it out. We'll measure RF values for every color we can see. In this example, I can see purple, I can see a black one, I can see yellow, and I can also see blue. There might potentially be a red chemical right in the center there, but it's a little bit difficult to see. But I can definitely see 4 distinct chemicals to measure their distances. The chemical distance of blue is going to be the farthest point it traveled. One of the things that the person in this example did not do, they didn't draw a line at the very top of the dot, the ink sample dot, with a pencil. Now lead will not separate out. It has to be with a pencil, not another ink pen. You need to draw a line right here, and that's going to be your reference point to start out your chromatography. Here's just an example of an ink chromatography all run on the same sheet of chromatography paper. There's a technique called gas chromatography. We don't have a gas chromatogram in the lab, but it's a technique for separating compounds based on their volatilities. And this is often used in the crime lab to test liquid samples or other chemicals in very small amounts, to break them down into their components, and it'll tell it, a gas chromatogram will tell you what is in a sample. The term volatility just means the tendency of a substance to vaporize. In other words, the tendency to change to gas. And we know that different substances change to gas a lot more easily than others. If you put a spot of water and a spot of alcohol on the table, the alcohol will evaporate much quicker because it has a higher volatility. Here are volatilities related to vapor pressure, and a higher vapor pressure means a substance is going to be a lot more likely to vaporize than a low vapor pressure substance. So you don't have to know this chart or memorize it, but because we can go to it for reference if we need to. There's a picture of a tabletop gas chromatogram that is a very expensive piece of equipment, but this is what you might find in a crime lab or in a research lab where they're using the gas chromatogram to separate out compounds. Here's a printout from a gas chromatogram that you would get, and you can see the peaks because of where they come off on the gas chromatogram. They're actually marked. This looks like a benzene peak, a toluene peak, an ethylene peak, etc. And we actually know what chemical compounds are in the sample that ran through the chromatogram. Here's a more detailed example that has 30 different identified compounds within a sample. This may or may not be useful depending on what this list tells us. There's a three-dimensional version that shows data on pens that can be compared. The FBI keeps data on almost every pen made around the world, and that allows them to identify ink samples, even a tiny ink sample from a letter or a card or something related to a crime. They'll go in, create a chromatograph, and compare it to all of their standards that they have, and they have thousands of standards on pens and ink. Here are some things that gas chromatography could be used for: to analyze body fluids, to detect illegal substances in a person's blood, to test fiber chemistry, to detect explosives residue, to determine the identity of an unknown liquid. These are all things that chromatography is used to do in the crime lab. Be sure that you jot these down and know several examples of what a gas chromatography lab can do. Just real quickly, here's how you can ruin your paper chromatogram if you fail to mark it with a pencil at the start, if you fail to mark the solvent endpoint with a pencil, because the solvent will soon evaporate and you won't know where it stopped. Allow your ink spot to be immersed in the solvent. That will cause it just to dissipate and not to run up the paper as it should. If you allow your paper to stick to the side of the glass, that will mess it up. If you measure from the wrong place in the end, be sure you're measuring every time from that pencil line you drew. Or if you just fail to record the right pen and get those mixed up, then if you didn't write it down initially on the paper and you go back later and try to remember, there's a very good chance you'll mess that up. So be sure you follow the lab procedure exactly. You need to record the lab procedure in your lab notebook along with your the purpose of the lab. Let's look at that real quickly. Read this background paragraph on the pre-lab that you have. Here's the purpose. You're going to be trained to use paper chromatography to separate chemicals found in ink samples, and you're going to be trained to construct the reference library of your own ink samples. Here's the procedure. We are not using the toothpick style. It works better if we just turn the edge of the paper over at the edge of our beaker, and that's what we'll be doing. So you don't have to rewrite every word of this procedure. You can make it in shorthand, but when I see it, it needs to represent well the procedure, and you should be able to work from your lab notebook as easily as from here. This is right here is in bold letters for a reason, and that's because that's important. If you don't do that, then your data will be meaningless. Use a pencil and make a mark, okay? Be sure, again, the ink dot stays above the solvent level, okay? Once the solvent is moved more than halfway up the strip, okay, it gets within about a centimeter of the top, you'll remove it. We'll have to get started right away because some of these take a little while to run. This is explaining how to calculate RF values on part 2, okay? Again, you don't have to write this whole procedure. For example, number 1, you don't have to write the sentences that are not describing the procedure. You just need to write down what the procedure says. Like this on number 2, look closely and determine how many different chemicals are in the sample. Once you get your procedure written down, be sure that you bring your notebook to class. Make sure you understand what RF value is, and if you have questions, I'll answer them there. This is a really cool lab, and I'm looking forward to doing it with you.